Hi everyone. So this video is about the cost function. So we'll discuss what's the important principle guiding the choice of the cost function, or as we discussed last time, it should be more accurately described as a cost functional because it's for every choice of the parameters you get a function of the input that gives you the output, and then the cost is a function of that function that the model defines, right? So let's see so the main principle that guides the choice of the cost function is a principle well known in statistics that's called the maximum likelihood principle. And the principle is very simple. So let's say I have a set of input vectors, x, and I have a set of labels associated with them that are available when training, right? And so this is again a classification problem, and you want to choose the model parameters. So the maximum likelihood principle says that you should choose the parameters theta that maximizes the probability of observing the labels y given the input vector x, right? So that means that I choose the parameters that maximize the likelihood that my model will output the labels given by the labels given to me in training y given the input x, right? So we choose these parameters. So actually, to be more accurate, this p here is the p model, right? So this is the probability that the model outputs the labels y given the input vector x. Okay, so let's play with that very basic equation. So theta ml is the argmax theta p of y given x and theta, right? Now there are two key assumptions that can help us significantly simplify this equation and get a very simple formula that gives us an insight on how to design practical cost functions, right? So the first assumption is that, so let's say I have n examples. So I have n x's, x1 to xn, and correspondingly I have n y's, y1 to yn. X's are the input vectors. Each x can have multiple components, so do not confuse the xi here with the features. And you have the labels corresponding to each x. So you have n examples, right? So n is the number of examples. Right? So the first assumption is that the yi's, the labels, are conditionally independent given x. Meaning that if I tell you the whole x, the whole n examples, x1 to xn, then the y's are the distribution of the distribution of each y is independent from the other y's, right? So if I give you all the x's, let's say I have 20 examples. If I give you x1 to x20, then the distribution for y10 is independent from the distribution of y9, is independent from y8, and so on. So that's the first assumption. The second assumption is that x, xi, yi forms what's known as a Markov chain. So what does it mean, Markov chain, right? It means that the statistical dependence of yi on all the x's is captured through xi, right? So if I have 20 examples, then y10 depends on x1 through x20 through only x10, meaning that if I know x10, I don't need to know anything else about the other x's to determine the distribution of y10. If I know x9, I don't need to know anything about the other x's to determine the distribution of y9, right? So the second assumption gives us the fact that probability of yi given x and theta will be equal to the probability of yi given xi and theta, right? So I can replace the x by xi. And the first fact, the first assumption gives us the ability to decompose the joint probability of the y's given x and theta into a product of p of yi given xi and theta, and the product over all the examples from 1 to n. right? So if we have these two assumptions, the yi's are conditionally independent given x, and x, xi, yi is a Markov chain for all i's from 1 to n, then I can have theta ml equals argmax theta, the product of p yi given xi and theta. Now, if I take the log of this, the logarithm is a monotone function, right? So it means that it doesn't change the maximum and the minimum, right? So if I am choosing the theta that maximizes the product of probabilities, then it will also maximize the log of the product of the probabilities, right? Now, if we do that, so the reason we're choosing the log is that it has this nice property that the log of a product equals the sum of the log of the individual elements. So then theta ml will be equal to argmax sum I from 1 to n log pi given xi and theta. Now this, if I divide this quantity here, if I take it and divide it by 1 over n, nothing happens to the argmax, right? So the argument or the theta that maximizes the whole thing is still the theta that maximizes the whole thing multiplied by 1 over n. Now the nice thing is that when I sum these elements and then divide by n, n is the number of them. So I am taking an empirical average. So it's as if I am taking the argmax of theta over the expected value over the empirical distribution over the training data of x and y, right? So I take the joint probability of x and y and calculate the empirical value of it through the training data and take the expectation of this of the log of the probability of p model yi given xi and theta, and distinguish between this p model and the empirical p data, right? P model is the probability of the output of the model given the input of the model given the choice of the model, and p data is the empirical distribution of the given data in training. Now this argmax is the same as argmin, the negative value of it. Now this quantity, right, is called the negative log likelihood cost, and this is also known as the cross-entropy cost, and this is the cost that the maximum likelihood principle is suggesting when training machine learning algorithms. Thank you.